everybody that's not here. Psych, we're reviewing for the cumulative test and you are missing it. Okay, we are here. Because I wasn't going to. I feel like I'm kind of like giving in, doing that, but then gotta do it. Yeah, yeah. Okay, we're gonna go over any ones you want. I have a couple I'd like just to start with because I feel like we did them a long time ago, and I want to make sure you remember those. And then we'll, like for example, number 2. That's the kind you can just look at if you remember. Yes. Ooh. Okay. Okay. So how did you get it was 5/4? Yes, Jerry. Coefficient. Exactly. And then you only do this when you're taking the limit as x approaches positive or negative infinity. You compare the degrees, and if the degrees are the same, the limit is the ratio of the leading coefficient, so it'd be 5/4. Let me just show you a couple that you don't have, just that are similar. Okay. I just made a couple others up because that's one case. I made a little. Oh, does anyone need paper or anything? I have plain paper. Does anyone need anything? Yep. Paper drawer. You can just whatever you don't want. You can just put on that table with those things. Okay. So look at the first one. All right. Again, it's with all these, when you're trying to find the limit as x approaches either positive or negative infinity, you're looking for the end behavior. You're looking to see, and if it's not going to be 0 or some other constant, it's going to be positive or negative infinity, and you have to know which it is. So what about that first one? What do you think? What is your total guess? Yeah, it's 0. Agree? Yeah, the highest power called the degree of the numerator is less than that of the denominator. So whenever that's the case, and you're taking the limit as x approaches plus or minus infinity, what you get is 0, right? And that's when the degree of the numerator is less than the degree of the denominator. Take a look at the second one. Yes, Jess. I fooled you. Uh, Manny. Yeah, that was a good one, right? 5/3. Yeah, they don't have to be in order. Sorry, she already gave you the answer. Oh, okay. Yeah. No. The only time it's going to do anything is when is in the third case, which I'll get to. But if the degree in the numerator is less, the answer is always 0. If degrees are the same, if the degree of the numerator equals the degree of the denominator, then it's always the ratio of the leading coefficient. So I put them out of order. Leading is to be it's got to be the coefficient of the highest power term. So this one would be 5/3. And it doesn't matter whether we're talking positive or negative infinity. But in the last case, all right, now we have a situation where the degree up top is greater. Degree of the numerator is greater. So it's not that the y's aren't going to 0. They're not going to some finite value. That means as the x's go to infinity, you got two choices. It's either going to positive infinity or negative infinity. But now which one? What do you think? You think negative infinity? How'd you get that? That was awesome. Yeah, when the degree up in the numerator is greater, you're going to get positive or negative infinity. Oops, I don't know why I wrote that. Negative. Greater than denominator. So your answer is always going to be positive infinity or negative infinity in this case. So technically the limit doesn't exist. But the way you determine which one, she's right, this one's negative infinity, you look at the sign of the leading terms. Now, if x is approaching positive infinity, a positive cubed is positive, and you look at the leading term in the denominator, and this would be negative, so positive over negative is negative. See, if this had been approaching negative infinity, then the limit would have been positive infinity, because then you would have had a negative over negative. If x was approaching negative infinity, so if x was approaching negative infinity, again, I would know it was positive or negative infinity because of the degrees, but the numerator, if that was a negative infinity, would be negative. The denominator would be negative. So it would have been positive. So that's how it would have affected this. Yeah, I'm just going to go over a couple that I think you might have forgotten because these are old. Oh. Piecewise functions, number 15. All right, so what does it take for a function to be continuous? There are 3 requirements. Now, first of all, what's the only value we have to worry about? 2, because everywhere else is no problem. All right, what were we going to say, Gina? Okay. Okay. So the limit has to exist, has to be approaching the same y value. So the first thing we have to make sure is that the limit as x approaches 2 from the left has to equal the limit as x approaches 2 from the right. So we got to check that first. We got to make sure for it to be continuous at 2, you have to be able to draw it there without lifting your pen off the paper. So the y's have to be approaching the same value. How would I figure out what the limit is as x approaches 2 from the left? To the top one, right? That's when x is less than 2. If you plug 2 in there, to the top branch, 2 squared plus 5. Okay, that's 9. How about the limit as x approaches 2 from the right? Actually, plug 2 into the second branch, 7 times 2 minus 5, it's also 9. Okay, the limit exists. That's one of the requirements to be continuous. So we know our graph is approaching the same y value as x gets closer to 2. But what's something else that has to be true? Because it could be approaching the same y value, it could be a hole there, right? Nope, not to be continuous. Yeah, this is just, we always got to check that first. Yeah. You want it to be continuous. So far we know that as the x values approach 2 from either side, the y's are approaching 9. Okay, that's nice. But we want it to be continuous. Yeah. Still could be a cusp, and it would still be continuous because you can draw a cusp without lifting your pen off the paper. Okay, it has to be continuous. It can't have a discontinuity. No holes. What do you want y to be when x is 2 so there's not a hole? Well, we know that the y's are approaching 9. Like if this was the y-axis and that was a 9. If the y's are approaching 9, as the x's get closer and closer to 2 from each side, and we want this to be continuous, what would you want f of 2 to be? 9, right? So you have to get first of all, you got to make sure that f of 2 exists. See, does f of 2 exist with this piecewise function? Yeah, because there's an equal to. If there was no equals, f of 2 wouldn't exist. It could never be continuous at 2. But it does. And what is f of 2? 9. And the third condition is, not only does it have to approach the same value from either side, so the limit exists, it has to equal the functional value. 9. Everybody's 9. So as long as... See that? She missed the 9 day. So yeah, it's true that the limit of this function as x approaches 2 equals f of 2. So now we know that it's continuous. But just because it's continuous doesn't mean it's differentiable. It has to be continuous to be differentiable. But if you get any kind of a corner or cusp, the derivative won't exist. So, I mean, if I found in this part that it said that it was not continuous, I wouldn't even check to see if it was differentiable, because it can't be differentiable. So the first requirement to be differentiable for the derivative to exist is that it's got to be continuous. Now I know it's continuous. Let's We already know that. Now it's continuous. We want to make sure, too, there's not a corner or a cusp. Does anyone remember what you do with the piecewise functions? You do take the derivative, okay? You take the derivative of each branch, and you're going to do the same thing. Well, what's the derivative of the upper branch? Yeah, so the derivative is 2x when x is less than 2. What is the derivative equal when x is greater than 2? 7. And I never assume, like, with the equals, if I'm trying to figure out if it exists there, I'm not going to assume it is that. So, okay. So, you want to make sure that as you get really close to x values of 2, that the slope's approaching the same value. So, let's just do the same thing. Let's look at the slope, the limit of f prime of x, as x approaches 2 from the left. What's the slope going to be as you get closer and closer to 2 from the left? 4, right? Because it's 2 times 2. All right, so I know as I get closer and closer to 2 from the left, the slope is approaching 4. How about the limit of f prime of x, the slope, as x gets closer to 2 from the right? Oh. So from one side, you get closer and closer to 2 from the left, the slope is approaching 4. And then from the other side, it's 7. Uh-oh. Right? Is the derivative going to exist at 2? Nope. It's not the same. So this would be an example where it's continuous, but not differentiable. The derivative doesn't exist at 2, so it's not differentiable at x equals 2. I think there was another part to that question where they asked if there was a max there or something, or a min. Well, a max or min? Well, first of all, to have a max, the derivative has to go from positive to negative. And then to have a min, the derivative goes from negative to positive. This is just positive to positive, so it's neither. Yep. There's a hole, it's not continuous. The limit could exist. If you have a graph, okay, right here, the limit exists as x approaches that value, but it's not continuous. Because to be continuous, not only does the limit have to exist, but f of that number has to exist, and it has to be the same. Okay. Okay. What else did I think was good? Oh yeah, I just made up another one. We don't need those. Oh, number 31. Yeah, I wanted to go back to that old stuff first because I thought, yeah, we all are going to, but that's why we're enjoying the time while we're here. And multiple choice. I know this is not what you have on your paper. You're going to 31, but just look at what I have up here. Remember when we first started talking about the derivative? Like even in pre-calc, you started with the difference quotient, right? And then we said, oh, that's the slope between 2 points. Let's make h, the distance between the x values, approach 0. So now we're talking about the slope at a single point. That's the derivative. This is the definition of the derivative. Remember that? The limit as h approaches 0. Okay. Well, whenever you're asked to find the limit as h approaches 0, and it's in the same format, remember what this whole limit equals. It's always always equals the derivative of that function over there. Now, this one has a number plugged in. Okay? But to do problems like this, you can't just plug 0 in for h. You're going to get 0 over 0. Yeah. Yeah. Yeah, after the minus sign, the first thing you should do for these, it's like a 3-step, it's either a 2 or 3-step procedure. Always identify what f of x is. Now, if they put a number in, just imagine the number they put in as an x. So the function that this would be f of x. That would be the minus f of x. Now remember, this whole limit of all this equals the derivative of that function. So the second thing you should always do is take the derivative of that function. What is that? Secant. And if, like sometimes you're done, because they just say, if that was an x there, would you be done? Yeah, but if they put a number in, you got to put the number in. So we got to actually plug the number in to the derivative. So it would be the secant squared of pi over 6 pi over 6 radians. How many degrees is that? 30. So this is like saying 1 over the cosine of 30 degrees squared. Ooh, that was very good. Because cosine of 30 is rad 3 over 2. Oh, okay. Alright, I was like, wow, that was fast. Yeah, cosine of 30 is rad 3 over 2, so you flip it. So it'd be 2 over, well, I'll write it down. 1 over rad 3 over 2 squared is just 2 over rad 3 squared, or 4/3. Can I just see if you got that with another one? Mine? But the other one I have here is, they didn't put a number in, so it's actually even a little easier. Saves you a step. So you're going to put in a limit as h approaches 0, cos squared of 3 times quantity x plus h minus cos squared of 3x over h. Now, what's the function? Cos squared 3x. Now we know that this whole limit just equals the derivative of that function. Oh, bless you. So we just got to take the derivative of that. I got to do something before we take the derivative. What should we do before we start taking the derivative? Yes, Cameron. Yes. You want to rewrite that as the cosine of 3x, all of it squared. Because this will remind us, what do we need to use to get the derivative of? Chain rule. Let's see if we can get this all right. We just sighed. Okay, what do we got? First layer. What? Okay, yeah, leave the inside alone. Okay, good. Next layer. Oh, negative side of 3x. That's right. Now, this is a multiple choice question. They're probably going to multiply the constants and put them out front, right? So probably it's clear negative 6. And then sometimes they put the sign first. I don't know why. That's not alphabetical order. It could be either it could be negative 6 sine 3x cosine x or the other order, but I'll just write like this. But they'll definitely multiply the constants together. Mm-hmm. Yeah, I may just be focusing on all the ones that aren't going to be on it. Maybe. Maybe not. Maybe not. Alright. You okay so far? We have to be. You have no choice. No, this one, forget about that. Some other kid asked that. Oh, this was the related rates. But that, you know what? Don't worry about it. You don't even have to worry about that. This one we already chain rule, we just talked about. You already showed me, like number 10. I think you could do that. You already just showed me you didn't know that one. Not smart. Not smart. What the heck? You're here. You get rewarded with some knowledge. Also, people at home that are listening to this get rewarded with the knowledge. No, really, reads. Okay. Should we? This is get the second derivative. I don't know. You want to do this one or not? You do, heck yeah. We'll get the first derivative. Rewrite it so it's chain rule friendly. It's got to be chain rule friendly. You're not going to know what to do. So it's 2 cosine x. Get that wrong. Don't you get negative sine x. I'm going to put the negative out front. So it's negative 2 cosine x sine x. Oh, we're definitely not doing this one. Because what do we have to do to get the second derivative? Product rule. Alright, and then you plug in pi. You really want to do this? Product rule? Okay. Product rule, we'll consider the negative 2 cosine x as the first, and we'll consider the sine x the second. Alright? Product rule. First, negative 2 cosine x times the derivative of the second times cosine x. I should have just written plus the second. What's the derivative of the first going to be? Times 2 sine x. And then we just got to plug in pi. Right? What's the cosine? Here's pi over here. What's the cosine of pi? Negative 1. So we want to get the second derivative at pi. So we have negative 2 times negative 1 times negative 1. Right? Cosine of pi is negative 1. Plus, what's the sine of pi? 0. So don't even worry about it. It's negative 2. Okay? Good? Better than good. Let's do something else. Oh, I'll tell you right now, there is an implicit differentiation. Because there's one on every... Oh, no. Oh, you look sad. You're like... And you failed? Alright. Implicit differentiation. First of all, it's finding dy dx when you don't start with y equals, okay? It's, x is in y. You take the derivative of both sides. You get all the dy dx terms on the left, right? Move everyone else over and factor out dy dx. You want dy dx. The question reads find dy dx. So you're going to take the derivative of both sides. Yeah. I can even try to solve for y with these. Alright, so let's start with the left side. What's the derivative of x squared? Now, this is the part that you got to be careful with. The next term is a product. Okay? So to take the derivative of the second term, you got to use product rule. And if you don't want to have to distribute a negative later, just consider the negative 2x to be the first. It's like plus negative 2x times y. So negative 2x is your first in your product rule, and y is your second. So we're going to write out the derivative of that. So we're going to do first, negative 2x, times the derivative of the second, y dx. Plus the second, times the derivative, yes, times negative 2. I just want to write negative 2y. So that's weird. Oh, too late. Can't. Negative 2y. Alright, so far, we've taken the derivative of the x squared and the negative 2xy. Now we still have to take the derivative of the plus 3y squared. plus 6y times dy dx equals 0. That's one of the biggest mistakes people make. They just write the number on the side. They don't take the derivative. Okay, so, and you don't have to do this in a million steps. You know you want all your dy dx terms on the left and everyone else over on the right. You might as well factor out the dy dx while you're here. So if I were only talking about my dy dx terms on this side, and I factor out the dy dx, it's going to go in the parentheses. Negative 2x. You can do whatever you want. Yeah. 6y minus 2x. Yeah, I like that too. All right, now, the other terms that didn't have a dy dx, they had to be moved to the other side. Oh, so it'd be 2y minus 2x, right? And then you divide. Yeah. Now, and then you look and say, oh no, my answer's not there. You can factor out a 2. So we have y minus x. We have a negative x plus 3y. And they say, oh no, it's still not there. A lot of times they put the positive term first. And you see in our denominator, yeah, a negative x plus 3y is the same as a 3y minus x. Putting the positive term first usually helps you to match things up. That's probably the one. 10 multiple choice and one free response. Yeah. Okay, you ready? This is gold, people. This is gold. Yeah. Alright, so you know that. We don't need to practice that again. I think you know that, right? Now. Oh, this is... I think, was it yesterday I said, how do you write the equation of a tangent line? Write the equation of a tangent line or a normal line. So you got to know how to do that. Now, sometimes... I mean, they always have to give you where you're going to write the equation of tangent line. They always give you your A. Sometimes they give you the y-coordinate of the point 2. Right? But you have to know, to get the slope of the tangent line, you got to get the derivative and plug in the value they give you. If it's normal, if it's the normal line, you do the same thing, but the slope is a negative reciprocal of the derivative there. So we'll do one like that. I know the one they had on was kind of ugly. Yeah. Radical and something else. Was there another one that writing the equation tangent line, one of the parts? No? Not in the second part or something? No? Alright, we'll do that one then. Oh, and one of the free response questions, number 5, it was the first question, is part A. Number 13. 13 is just the slope of the tangent line. That's just the derivative. That's implicit differentiation again. 13 was another implicit differentiation, because find the slope of the tangent line just means find the derivative. Alright? And then you got to plug in the coordinates after you get it. Alright, I want to do one of these, write the equation of a tangent line or a normal line. So we can either do one like in the free response, 5A, or in the multiple choice, was it number 8? I think, yeah, number 8. You want to do 8? Okay. So 8 is the normal line, but let's say that let's write both, the equation for the normal line and the tangent line while we're there. Because once you get the derivative, it's easy. Okay? It's number 8. So they ask us just for the equation of the normal line, but I'm going to do both. Y equals... Alright, we're just going to write this as 3x squared plus 2x to the half. And at the point is 2, 4. For that, they gave us the x and the y coordinate. If they didn't give us, if they just said write the equation normal line at x equals 2, we have to plug the 2 in to get the 4. But they help us out. Yeah? It's nice. Alright, so whether it's the tangent line or the normal line, you got to get the derivative. So what do you got for the derivative? Nice. Okay. Now, as far as me plugging in the number to see what the derivative at 2 is, because x is in it, so I need the x coordinate of that point, I'm going to rewrite it. I'm going to rewrite this. In the numerator, I have a 6x plus 2. What do I have in the denominator? 2 radical 3x squared plus 2x. Okay, so that's my derivative, right? We want to plug in, since there's only x's. What's that? Really? Oh, if you're using your calculator. Well, just so you know, like I'm gonna let you guys use your calculator tomorrow, but on the real AP, you can't use your calculator. You know. Yeah. Yeah. And they'll tell you. Okay, so let's plug in the 2. I'm plugging the 2 in. If you plug 2 into the numerator, what do you get? I was scared. Okay, so 14 over 2 radical. That was scary. 12 plus square root of 16. 8. So we have 7 over 4. Okay, so we have 7 fourths. Now, let's write the equation of the tangent line. Then we'll write the equation of the normal line. So we got the point, 2, 4. We got the slope of the tangent line, 7 fourths. So if they did, I know they didn't, right? Ask us the equation of the tangent line. What's it going to be? Y minus 4. Uh-huh. Nice. Okay. And then if they ask for the equation of the normal line, like they did here, y minus 4, negative 4 sevenths, x minus 2. So that's the equation of normal line. But then you look at the choices. Oh, no. Okay. Well, here's what you do. First of all, you notice none of the choices have fractions. So we can multiply both sides of the equation by 7, right? So we multiply both sides of the equation by 7. We have 7y minus 28 equals, I want to see what you guys write for this, negative 4 x minus 2. Well, you can distribute when they're over addition or subtraction, but not over multiplication. Oh, you did. Okay, that's good. Sorry. Now, so one thing, so I got rid of the fractions by multiplying each side by 7. The other thing is you look at the choices. All the x's and y's are on the left, and the numbers on the right. So you put your x's and y's on the left, and the number on the right. Yeah. The no calculator questions are about 2 minutes a question. Okay. The calculator questions you have about 3 minutes a question. Yeah, they give you more time for some reason for those. But these are about 2, but some of them are really, really fast. Some of them take longer. So it's like on average. What's that? Number 7? Yeah, like that. If you know your derivatives, that'll take you, 15, 20 seconds. Something like that, Yeah. Um, well, you could have that point on different lines, and it doesn't mean it's the normal line. If you get, I mean, you could get rid of some, you could get lucky, and maybe they didn't think of that, but usually they're pretty clever, though. figure out ways. Wait, what did I have with this? I don't even know what 16 was. Let me just see. I don't think this was important, but let me just see what that was. 16. Oh, local min, max. Actually, I did. Okay, this topic, like 16, I want to make sure you guys know whether it's a max, a min, or a point of inflection. What do you do to find, if they give you a function like it's 16, what do you do to find relative max or min? First derivative, okay. Then you got a factor, get the critical values, and what do you make? A little sign chart. And if the first derivative changes sign, you got a max or min, depending upon the order. Oh, that's nice. Second derivative. Yeah. Negative to positive. Well, slope goes negative to positive, it's a min. Positive to negative, a max. If you're looking for points of inflection, like I think one of the free response questions had that, you got to get the second derivative and make a sign chart. So for this one, for 16, are you okay with that, or should I just do this one real quick? So you get your derivative. If they ask you for extrema, you know you're going to deal with your first derivative. Critical values, values where you could have a max or min, where the derivative is 0 or undefined. Well, it's always defined. So you just factor to see where it's 0. A little sign. So the only places the first derivative could change sign would be at -4 and a 10. Now, this is the question I always get. Wait, when you take a test value, what do you plug it into? If this is a first derivative sign chart, try to find the sign of the first derivative, it should be plugged into the first derivative, right? Well, if you're trying to figure out the signs of the first derivative, see, we know that the only places it could change sign is right here and here. So any point you pick over here, any value of x greater than 10 is going to have the same sign as the first derivative. But to get that sign, plug it into the first derivative. Right? So see what it is. We plug it into the factored form. So everybody's going to be positive over here. Everybody, all the factors are positive for those x's. Number between -4 and 10, such as 0. Negative. A number like -5, it's going to be positive because it's going to be negative, negative. All right. So what's happening at x equals -4? Max. What if we had to get the y coordinate of that point? Like, what if we want to know what the actual relative max was? How would you figure that out? Into what? Original, right? So you'd have to, so we know there's a max at x equals -4, but to get the y, as always, you'd have to go back to the original. Okay, the other three, if I were you, I would look at u sub, like number 12, something like that. And number 6, area between graphs. Area, it's either going to be y top minus y bottom, or x right minus x left, the dy. Right? And one more. One more. Remember the number line technique? I forgot. Oh, number 32. Like one of those. Yes. Like I tell you the definite integral from 0 to 10 and from 3 to 10. Just make sure the lower limit of integration is less than the upper, or else you have to switch them. One that covered topics that were in here. And there's extra help today.